Hello everyone, this is Abdullah, and for this video I will show you how to do transient analysis on the inverter. So in the past videos, I uploaded two videos in the past. So the first video was about the setup of Cadence, and the second was DC analysis. So please check those out first and then watch this. So in this video, we'll start off by copying this schematic. Instead of just copying the schematic inside on another open cell view, I go for this. I just right click. So go inside VLSI test. We created this library. Inside that library, we have the inf cell. And inside the inf cell, we have the schematic and the Maestro. And Maestro is where you did the analysis, and schematic is where you edited or added the instances or the MOSFETs and the sources to analyze through Maestro. So for now, let's just copy schematic because we'll have to change a couple of stuff. So for this one, we'll have to name the schematic to another thing. Let's just name it underscore tran for transient, and then click on OK. This will copy the schematic, so we have another schematic here. So what we'll do now is right click and open. We opened another schematic here. So for now, maximize this, press on F to fit, and then we have a schematic now. So I want to do a couple of things. I'd like to delete these just to show you what I do when I create my own schematic. So my way is a bit different. Let's add the labels here. How did we add a label? It's just pressing L for a label. So let's add VDD, and then let's add ground. Ground with an exclamation mark just to make it global. And then click on hide. So we'll have VDD, have ground, attach it to those wires, and then press on escape. And the second step is to add the sources. So I press on I to add an instance, I for instance, and then navigate to GPDK. And then, for the sources, we have to do analog lib. And then what kind of source are we going to add? We're going to add the V pulse. That's one source. And the other source is VDC. So that's the other source. I'm putting it here. So instead of wiring those up here and there and make the circuit more complex to read, well, in this case, it's really easy to read it because we have only two sources and two MOSFETs. But later on, when you add multiple MOSFETs, like at least tens or maybe just 5 MOSFETs, things will start to get complicated and it will be harder to read the schematic. So in order to make things more easier, what I'd do is I would add a wire here. So I press on W for a wire. I clicked once, came here, double clicked, just to make it floating. And instead of just wiring those up all the time, I could just copy. So escape and then click on C for copy, 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 copy. And then I would label those to the corresponding nodes that they should be connected to. So in the case of the DC source, we will connect that between VDD and ground. So let's go ahead and press on L, VDD, and then ground, exclamation mark, click, click. And then for the pulse voltage, we'll have to connect that to in and ground. So click and click. There we go. We still didn't configure the sources, but the reason why I did this, it makes it more easier, less wiry. You don't have to see all the wires all around the schematic. When things start to get complicated, you'll understand even more. But for now, please use this kind of template, should I say, or maybe this approach when building circuits and analyzing them. Things will get easier. So the next step is, let's just configure this DC source and put 1, because our supply voltage is 1, the operating voltage for the 45 nanometer technology. And for the pulse voltage source, let's press on Q. So I clicked once and then pressed on Q. And for now, you don't have to put DC voltage for the pulse, but this is what we'll do, and I'll explain this later on. So for now, put in 1 volt. Let the period be 10 nano. This is a high value, but just for the sake of brevity, that's what I will do for simplicity. Delay time, put it net 1 nano. Rise time, something small, maybe 10 pico. Hold time, 10 pico. Pulse width. Pulse width for 50% duty cycle. If you want even or equal high level and low level logic of the pulse, you put the pulse width as half of the period most of the time. Well, in digital circuits, they always, I mean, not always, but most of the time work in a 50% duty cycle. Or maybe for analysis, most of the time you want to use 50% duty cycle for easier analysis. So for now, put in 5 nano. We will not add anything else. So just these 7 values. All right, 7 parameters. Add them, and then click on OK. And then save the circuit. So for now, we have the circuit ready. What we will do is we will launch, and then Explorer, and then open existing. Or you know what? Just for this, I'd like to create a new one. So let's create a new view. So Inv Maestro, and then I'll just rename this, or actually for the new Maestro view, I'll name it as Maestro_Tran. And I'll select New tab. Takes a while for this to open, but I have to wait a couple of seconds. All right, so we got this open now. So the first thing is you want to select the plots, what you want to plot. So to be plotted, select on design. So we'll take you back to the design. I know it's a bit slow, but it takes us a couple of seconds, just as I said. All right, click on in and then click on out. And that's about it. You don't need to plot anything else. And then click on or press on escape. And then navigate back to Maestro_Tran. So now you got both of these signals. All you have to do is click on save. And now we have to add the analysis, which we did for the DC part, but now we are adding the transient. So in the last video, we used this. We added the component or the source, the voltage source. We had at the input and then saved the DC and all that. But for now, we'll click on Tran. So this is the stop time. So the simulation time, or basically the maximum time you want to plot all the waveforms. So my period of the signals period is about 10 nanoseconds. So what I want to see is maybe two pulses of that, or 2 periods of the signal. So I'd go for 20 nanoseconds. Don't click on this. If you want, you could click on moderate, conservative, liberal. For conservative, it will just give you more accurate results. Moderate, less than that. Liberal, very less than the accurate results. But yeah, for now, you don't need those. No, don't click on transient noise. And yeah, that's about it. So 20 nano, and then click on OK. And then let's run and see what's happening. Did we save the circuit? I don't think we did. I'm not sure. Did we check and save? Let's do that again, just in case. Yes, we checked and saved. We didn't have any problems in the circuit. Go back to Maestro. All right, so in Maestro, we have everything done, and just click on the run button. As soon as I clicked the run button, this popped up. The log file, basically. And I got the signals. So you got this graph, but it's a little bit confusing, especially when you have more signals, right? So in those terms, let's say you have more signals and you want to view every one of them in a different panel, right? Or in different window, let's just say. So you have to do is click on this. This will separate the signals so you can view them easier. If you want to combine them again, you can click on this and you combine the signals. So let's separate these for now. And you'll see this is the input, or the pulse voltage we gave it. And this is the output. And the output is swinging from 1 volt to 0 volts. We got spikes there, or maybe overshoot and undershoots. It doesn't matter for now, but yeah, it doesn't matter for now. We'll just have to analyze what this is. So for now, I want to show you, the results of the configuration of the pulse voltage source. So let's go back here. I want to show you just this. We check out the pulse voltage source on the inside. So you can see we did what we did is 0 to 1 volt. The voltage 1, the initial voltage is 0. The final voltage is 1 volt. The period of the signal is 10 nano. The delay is 1 nano. Rise and fall, and then pulse width. So I'll go through all of these one by one, just so you understand why I put these values. Now, this is not standard, but if you want to go with this all the time to analyze your circuit, you could do it. There's no problem with that. But for now, why did I put 0 and 1 here? So what 0 and 1 here define is, but it won't by side by side. Put the waveform side by side with the properties here. Yes. Oops. And this maybe. Yep. So this is the input, or the pulse voltage we gave in to the inverter, right? So what I did here when it did 0 and 1 volt, it is actually this voltage. So basically the first voltage you gave it, and the final voltage would be the higher level, or the one logic of the pulse voltage itself. If you do 2 volt to this would have gone to 2 volt up. And the period is defined between this point and this point, or this point and this point, or this point and this point. So that's the period. And between that and that, it's 10 nanoseconds. You could just put your cursor on it and you could understand that's 10 nanoseconds. So 6.02 nanoseconds and 16.02 nanoseconds. So yeah, that's basically it. The 1 second of delay time is optional. You could either put it or not, but the 1 second is defined over here. So this is the 1 second that we have. Is how much delay you would want to put to the signal before it goes to the final voltage or voltage 2 from the start of the simulation. So this is 1 second, 1 nanosecond. So it starts from here as 0 and it goes down here to 1 nanosecond. The rise time and fall time represent the rise here of the pulse and the fall of the pulse here. You could zoom in by right click and hold, and you could actually see that over the signal. So you can see here it starts from 1 nanosecond and it goes to 1.01, which is basically 10 picoseconds. 1.01 nanosecond is, or 0.01 nanoseconds is 10 picoseconds. And so the difference between these two in the x-axis, these 2 points, is 10 picoseconds. It's the same for the right side of the pulse or the falling part of the pulse. So if you come here and check that, you will understand that it goes from 6.01 nanoseconds to 6.02. So that's the full time of 10 picoseconds. And lastly, the pulse voltage. So let's fit this by pressing on F. The pulse is the time interval between the pulse itself. So that's half of the period in this case, because I put it as 5 nanoseconds, right? So here and here. So these two, the difference between these two is the pulse width. You could just understand this, or actually, let's just put it. So in order to put it, so this is called a marker. In order to put this marker, you have to press on, so bring the cursor, whatever you want to measure that value, and then press on M. And this will put in a marker. So another good tip is to put in a horizontal line. So a horizontal line is by pressing on H for horizontal. So this is a good cursor as well. And you could put in a vertical line to measure the signals in between these two. The vertical is V for vertical. Yep. And you could measure difference between two signals. And that's about it. So you want to see whether the pulse width is, on the markers or on the cursors, you could do this as well. So click on the cursor. Yeah, the horizontal cursor is called H1 because we have one cursor right now. And this is the Y position of the horizontal line. So you could actually change this to half of the pulse voltage, which is 500 millivolts, just 500 M, and then click on apply. And you change that to half of the PDD. You can see here is, so if we close this, let's go close this one. The pulse width, let's delete this one and delete the marker. So the pulse width, you can see here it's 1 nanoseconds or 1.005 nanoseconds. And you can come down here and see it's 6.015 nanoseconds. So basically you got approximately or somewhere around 5 nanoseconds of pulse width. The reason why we have this difference, even though we are on the same level, is because of the rise in the full time we have in between those two. All right. So let's go forward with, so I explained everything here. And you could realize another thing is the output of the inverter. So we gave in the input as, let's just say 0, 1, 0, 1, 0, right? So as far as the input is given and observing the output, we could see that it's the inverted signal or the inverted values of the input, because we're basically using an inverter circuit. So this is 1, 0, 1, 0, 1. And that's about it. So that's how an inverter functions. It inverts the input signal to the output. And that's transient analysis for you.